exercises, but as we only will have this session and another 4 sessions, I have decided to switch the mode of the exercises a little. In the recent years, the exercises were always accompanying the lectures very strictly. Because things are a little different, I have decided that we will just address the big exercises, because these exercises are quite similar to your exam. Okay, so in the end, in order to pass your exam and to get good grades, you should be able to solve these exercises, and representative of these are, for instance, exercise number 59, which is a design task for power electronics. Then I go ahead. I have the exercise 60, system development. It is a gas analysis sensor, and there are more possibilities. Here we have one thing, which is a thermoelectric generator. This will be definitely not in the exam. So that's for people who are generally interested in the topic and who would combine their knowledge on MEMS with knowledge on assembly and packaging. But here we have one thing different. It's number 62, inertial sensor system. So you have to develop a gyroscope. And what else do we have? Yes, these were the 3 principal types. And I must say, your exam will be similar to one of these exercises. Okay? And now I would like to tell you what I expect from you. So today's session will be mainly, let's say, an introduction to that solving of the exam. So what would you prefer, power electronics, gas analysis, sensor, or a gyroscope? Can you give me a guess? What's your preference?
Whichever is the easiest.
I would say maybe the gyroscope is closest to what we have had in the lecture up to now. So my idea is we could do exercise number 62, which is the gyroscope or inertial sensor system. Okay, we have seen such sensors with 0-level packaging, 1st-level packaging, and so on, 2nd-level packaging. And so let's go through that task description. You have to develop a 2-chip solution of an intelligent gyroscope consisting of different elements. And we have a sensor device, which is a micro-machined gyroscope, which has 0-level hermeticity. We have a specification of the chip, which is 10 by 10 millimeters square. We have a maximum operating temperature of 125 degrees centigrade. And the permitted maximum stress in the sensor after the assembly is 75 megapascal. Okay. That means you also will have to perform some thermal simulations and some stress simulations, but the details we will see in the following week. Okay, now let's have a look at the controller device. The microcontroller is an ASIC, which has an analog part. It has a frequency of 1.5 gigahertz. Again, that will be important because it will affect the electrical parameters of the device. Now you are free to do a different design. You can have a controller device which is available either as a bare chip in flip chip version or as a surface mounted device. We have a dissipated power of 10 watt permanent and an assumed ambient temperature of 50 degrees centigrade. Okay, that's clear. The power dissipation leads to a certain increase of the temperature. On the other hand, we have the environmental temperature, and both temperatures add up to the final temperature, and that must not exceed 125 degrees centigrade for the sensor. And here, in that case, for the ASIC, not higher than 135 degrees centigrade. The lowest temperature which our system can see would be minus 25 degrees centigrade. The assembly must survive more than 1,500 temperature cycles for this delta T. Okay, in the lecture we will still see what the influence of temperature cycling is on time to failure. And another information is the longest digital conductor line is 72 millimeters. Okay, and now your task. You have to make a concept for the module with the listed components. You are responsible for the following selections: the substrate, the mounting techniques of the components, the interconnection technologies, the housing or encapsulation of the microcontroller, or either as chip or SMD, the zero-level housing of the sensor chip, the protection of the complete assembly, the cooling concept. What we would not like to have is a liquid cooling due to several reasons. Aspects are, first of all, it is important to make sketches which provide a total system overview and, if necessary, detail views. I want to see all relevant materials, also the surface materials, including one reason, so that would just be one word, why you used the material instead of another material. Descriptions of the manufacturing sequence and of the individual fabrication processes. With the design, you must solve following technical problems: thermal management, so it must not become too hot; solder joint reliability of the controller, it must survive 1,500 cycles; analyze the stress in the sensor chip and keep sigma under 75 megapascal; calculate the time of flight of a digital signal and check whether it is necessary to apply the transmission line model. Again, all of these calculation tasks we can do later. And so important is to have a proper sketch. Also, we need some formulas. All of the formulas are will be treated, or some have been treated in the lecture notes, and you use appropriate data for geometry and materials properties. So at least, let's say, the order of magnitude of these properties should be correct. And when you get all of these, when you have done it all, you get 90 points. And now we have the 4 criteria. It must be possible to manufacture it. It is a maximum temperature, it's a maximum stress, and the number of cycles to failure. When you meet the criterion, you get 2.5 extra credits. So in most cases, the credit for manufacturability will be met. So it's up to 10 credits you get by staying within specifications, and the total, as in all of my exams, is 100 points. Okay. In the exam, you will have 2.5 hours to solve this. In fact, it is typically possible to solve that thing. And also, I must say, maybe 5 years ago, I had a different type of exam where I had quite independent questions, and the exam became even a little better by having this one task to solve here. Also, one thing is important. When you have a special solution, for instance, you use a special die attachment method to mount the chip. Of course, all of your solutions should be consistent. Yes. Some people, they just take individual solutions, but the solution for the thermal has only a limited connection with the solution for stress, for instance. Of course, that is not what I expect, yes, but it should be a comprehensive solution you get here. Okay, so you understood what I expect from you? Okay, you're still here? Okay. Are you shocked a little by this question? You became so silent. Okay. Okay, but it's not a problem. Please, if you speak louder and speak slower, because otherwise I will hardly be able to understand you.
Maybe the question is quite it is quite strange for me. I'm not sure from the others, but I think we have to get used to those steps on how to solve the problem. So at least you can give us a sample or go through the exam to see what will be the step and what's the expectation from those who design.
Okay. Yes. So, in the end, in my exams, so typically the average is something like 2.1 or so, the average of all results, and maybe out of 50 to 70 students taking that exam, maybe 2 fail. Yeah, so that's a typical situation. So I think it can be handled quite well, and there are quite a lot who have a 1 decimal somewhat in their result. I think this type of examination and exercise helps very good to get a general understanding. Okay, so maybe we just start. What do we need? We need a housing for the system. We need a housing for sensor and ASIC. What else do we? Maybe not just a housing. It just could be a protection of that. Of course, both must be mounted, so we need a substrate. For instance, a printed wiring board, and we need some mounting technique. What else do we need? We need interconnections. Finally, all of that must be closed. Okay, these are the main parts we have here. Maybe I first make a general sketch which just shows us how it could look, and then we can maybe go into more details. What is advisable is also to have a look how it could be produced, because that's a very good sequence we can have. For instance, we could start with a substrate. That substrate could be a printed wiring board, but it also could be some aluminum oxide. Okay, when we have such a substrate, we must in some way mount the chip. And for the chip, for instance, we must have metallizations, and of course we need for instance different landing places. Okay, so that's a substrate, maybe not yet too detailed, but what would be necessary then? We have a chip, which is what we have also seen in the meantime. That chip is in some way mounted, and on the other hand, we could also have some flip chip or SMD. That could be solder joints. And of course, we need some mounting material. We have seen already different processes like adhesive bonding. And there's one thing which was also mentioned was, for instance, the question of wafer level packaging. That could mean we have some lid here, and here in between would, for instance, be that gyroscope structure. Okay, that would be the wafer level, or zero level package. And now we are, at least in the concept, finished with that system. And typically such a board or a substrate with the chips on top could be produced by some manufacturer, and possibly you could even purchase it. Now the next question is, which kind of housing could we use here? Do you have an idea what kind of housing we might have? We have seen several options for such a housing. Can you give me a guess? What shall I take? Can you please speak louder?
Can we use a molding?
Yeah, we can do it. That could be possible. We can do it, but when we use a molding, we need something different here. Sorry? Sorry? Yeah, a plastic, but what else do we need when we do a molding? Yeah, what we need is a lead frame. Yeah, that is very much important. And in that way we could do it. So we always have many options to do this. In fact, I would propose, yeah, okay, let's go for molding, but for molding we need the lead frame. Yeah.
The operating temperature is under 25 degrees.
Yeah.
And we need to have some kind of factor of safety in the temperature with regard to the flash transition temperature of the molding component.
You must be sure, of course, that the device you have created here will be able to survive the molding process. Yeah. That's a very important part. The reason why I was, let's say, hesitating a little with molding is that molding process is very demanding, and one needs some things which have to be taken into account. But now here let's say the following. We would the 125 degrees centigrade, that can be survived by a molding. Yeah, that I don't think is really really the problem. But now let's go for that process. The next thing would be we need some interconnections. And these interconnections could be done by wire bonding. Okay, what we also need is some interconnection try again. Okay, so we have the wire bondings. A problem typically with molding is that the stress is not so low. So one of the options could be, for instance, to tolerate the stress. We have here another option. Could be we take a second material which is soft, where we first cover the chip, so this gyroscope chip has no has not the stress from the molding. But on the other hand, as we already have a lead frame here, in our case, I would recommend something different. I would recommend here we take another package type, and my proposal is we take a pre-molded package. Okay, what's the difference between pre-molded and molded package? Can you give me an idea? Yeah, one is thermoplastic material, and the other is a thermoset material. So what I select here is a pre-molded package, and in our case, because the heat dissipation is relatively high, at least we need some kind of heat sink. Underneath here. That could, for instance, be a copper. Again, it can distribute and carry away the heat, but something is again missing. We need here some mounting, and always if we have a pre-molded package, the best mounting method is to use a glue. Okay, so in that way, let's repeat. We started with a substrate. Of course, the substrate must also be produced. We start with a substrate. On the substrate, we have mounted this wafer level package chip, and we have mounted the flip chip. Then the substrate was mounted into the pre-molded package. It was glued, and then we could produce the wire bonding interconnections to the substrate and to the lead frame. And here we would be almost finished. Yeah. For instance, now what we could do is we could fill up the whole thing. Maybe that would be a good idea with some silicone material. Here it doesn't like to go inside for some reason. Yeah, I just have to change. The color. For some reason it doesn't like to fill it up, but so you must believe me, we have filled in Sorry, we have to wait a second because that computer got mixed up a little. Okay, let's hope it will. So, what else do we need? We have to get rid of the heat, and we also have to put a lid on it. What do we have to do? We have to weld in some way. So, for instance, here we need some weldments. And one thing which is also important is something which is important. We need some kind of heat sink underneath. So we have lots of heat and we must get rid of that. And to that purpose, there should also be something like such fins we see here. I don't paint them all. So now we are having already a quite good overview of the system. My proposal is that we already look a little more at the details. One thing is, for instance, such a lead frame typically is not just copper, but it is some it has some surface finish. Yeah. Also, there is, of course, a metallization under the gold bonding wires. One thing also I already forgot. Let's wait for the computer. Of course, this mounting has also in some way to be accomplished. Okay, so that system should already almost be finished here, and then we could have a look at the individual materials we must assign here.
Professor, can I have one question?
Yeah, please go ahead.
So for the molding, do we always need to have a lead frame?
Not necessarily. For instance, just to give you an idea, you could have the substrate, you have the metallization coming out here, and for instance, you could make a molding like this, and here you just have, let's say, the pads look out. You know, for instance, a card which you put into your personal computer, yeah? Just imagine that card would partly be overmolded, yeah? In that case, you do not need a lead frame, for instance, yeah? But in the case of a pre-molded packaging, you typically need a lead frame. Did that answer your question? Okay. Now let's have a look at the materials. For instance, that would be a thermoplastic material. We could say it could be, for instance, polyamide 6 or PBT. So that would be a thermoplastic material. Here that could be a laser weldment. What would be the material of a heatsink? What would you take here? Sorry? Yeah, for instance, that could be. Yeah, or you can also take copper. Yeah, okay. I would say that's the two materials we use here. For the plate here, in here, a good guess would be copper. Now let's have a look at the substrate. What could we take as a substrate here? Give me a guess. Yes, and what's the material of that? So it's typically epoxy. Yeah, so people often used to say it is FR4, but epoxy glass is better. So here we have the lead frame. What's a typical material of a lead frame? It could be, for instance, typically it's an alloy because it must be a little harder, for instance. And it has a surface finish that we also must mention, for instance, that is a nickel gold. So here you cannot directly see the gold, but it is a nickel gold. Typically the nickel is maybe 3 micrometer, just as a guess, and the gold could be, for instance, 0.2 micrometer or so. But that are just typical values. If you would write 4 micrometer for nickel or 2, that also would be accepted. Okay, epoxy glass, and if we have that, we also must mention that in between we have a metallization, and that would be again copper. Some materials are still missing. Yeah, go ahead.
In the metallization that you're putting above the substrate, does it work for all of that we use copper? Because I'm not sure, but I think you told something about the water volume.
Yeah, when we use other substrates, yes. So we will do this exercise now with a printed wiring board. But it could be that that's not the proper material because the thermal conductivity is not so high, yes? And when we have that problem, it could happen that the heat is too much in the chip and the chip could be too hot. And in that case, another material could be more sensible, like aluminum oxide. Yes, we will see it in the next lecture. And aluminum oxide is never covered with, or in such applications, it's not covered with copper. Yes. So also, for instance, on chip, you never have, in most cases, you never have copper as a chip metallization. Okay, but there are two materials which still have to defined. That's adhesive. And my question is, what do we use as an adhesive? Yes, we take epoxy. On the other hand, if we mount such a heatsink, if it's a larger area, it also could be another material like silicone, but epoxies also have the best thermal conductivity. So how many adhesive layers do we have? We have here one layer. We have here and also here we also have an adhesive, yeah? Okay. Now the question would be, why do we use the individual materials? Another material which we also have not yet seen is here the material of these balls, and that's typically an SAC material, which means tin, silver, copper solder alloy. SAC. So my proposal is we go to the next page and we look for the process steps. So what was the first step we were going for? The first step was the fabrication of the substrate. The second was the fabrication of the housing, including the lead frame. Because it's a pre-molded package. What else has to be produced? When we go back, not yet. First of all, we are looking for the parts which we need. Here. Yeah, that's good. The zero level or wafer and number 4 is also the heatsink. One thing which I also request you to do is the flip chip preparation. That's not yet the flip chip bonding process, but the flip chip bumping. So when you buy such a chip, it must have the individual solder bumps, and that must be produced by a special process which we will still see, and that is important. But when we have that, so that's the individual parts which we need, we can go into our process. So typically, when you have a normal assembly factory, that's all parts you can just purchase. Yeah? So you would design it, you purchase it, but then you have your own manufacturing, which means assembly and packaging. And in that way, what would be the first thing? For instance, we could either glue the chip on the substrate, or we do first the flip chip soldering. I would prefer the flip chip soldering. And then I would do the assembly of the sensor element. The reason you could do it also the other way around, first number 7 and then number 6, but I think it's better first to do the flip chip soldering, because the chip can easily survive that, but we don't know how this sensor would react when we heat it to 240 degrees centigrade or 260 degrees centigrade in a soldering process. So maybe it's safer for the chip. So what do we do then? Then we mount substrate in the package. What would be the next step then? Do you have an idea? What can we do now? What about the interconnections? What will we do then? Then we will do the wire bonding. After the wire bonding, we can fill up with silicone. Yeah. Finally, we mount the lid. So it's closed. And what's the last step? We must glue it to heat sink. Okay. In that way, we can see if we approach the whole thing systematic. We have already found a solution for this design, and also we had, let's say, maybe a little more than 50% of all credits for the design part of our exam. Also, the sketch is an important part. Unfortunately, I was not able to make the perfect sketch I would have liked due to technical problems. But also it is important to know about the materials, and at least to assign all materials to all packaging elements. Okay, so for today we are finished. I think you got a first impression, and from my side I think it would be a good idea if you address the other exam questions or the big exercise questions, and have a look and think about where you already have the knowledge to solve it, or where you do not have it. But in the end, what we were exercising today, you have the knowledge from this lecture already to know about these things. What we will see on the coming Monday is more about the details of the processes. So what temperatures do we have, and so on. But for today, I would say I'm finished. Thanks for your... Yeah?
I have still a question about the operating temperature of 125 degrees.
Yeah?
Some materials that you use there that have a plant transition temperature that is close to 125 to 150.
Yeah?
That affects the behavior of the ship afterwards. Because if it's going to be cut until 125, some materials have to start softening. That's considered, or how we tackle that problem?
Good question. That's on a case-to-case basis. For instance, just to give you an example, the adhesives. Almost all adhesives have a TG which is lower than this maximum operating temperature. In that case, it doesn't matter very much. What we do not want to have, of course, is, let's say, for instance, a substrate which has a lower glass transition temperature than the operating temperature is. Yeah, so for instance, for the chip, for the flip chip, a maximum of 135 is already on the border of what normal FR4 epoxy glass would tolerate. So maybe in that case it might be necessary to take a high temperature FR4, which has maybe a 10-15 degree higher glass transition temperature. So that always depends. If you would have made a molding, so a direct reactive transfer molding, it would not have been a good idea to use a molding compound which has a lower TG than the operating temperature. On the other hand, that's also not really a problem, because molding compounds typically have high glass transition temperatures of, let's say, 180 or 170 degrees centigrade. Okay, but it's always depending on let's say, which system it is, and what could happen by the fact when you go beyond the glass transition temperature. Okay, I have one last point. sometimes I gave you, sometimes I asked you something, and some of you gave me answers. In fact, I I do not even know who it was of you because I cannot see it. But these exercises have been recorded and will be put on the Ilias for some time. So the people who gave me response, they must allow me to put this on Ilias. So because their voice is on the internet. So if that is a problem for you, then send me an email. Yes. You understand my point? Oh, I hope so. Yes. Okay. So maybe I even have to send you an email where I state, okay, you have agreed that I put the recording on the Ilias. Also, my idea is that I will take these recordings from the Ilias maybe in September or so. So there is no more trace of it anymore. Okay. Thanks for your interest and your participation, and see you Friday. Okay.